Hi. Several people have asked me to explain electronic conspicuity as it affects general aviation pilots in Europe. Electronic conspicuity, or EC, refers to the use of electronic devices that broadcast and/or receive an aircraft's position, altitude, and other flight data. These devices help you be seen by ATC and other airspace users and see them in return. It's used to avoid mid-air collisions and loss of separation and to enhance situational awareness. Transmitting electronic conspicuity can be mandatory or strongly recommended in different airspace and in different countries. I'm going to try and help you decide what's the most suitable technology and equipment for you to use and how to best use it. I'm going to explain quite a complex domain, but when push comes to shove, there are not that many possible solutions, and the choice between them is rather straightforward. Indeed, even just making this video has made me realize just how few options there really are. It's a confusing topic, so let me give you a very brief history of the evolution, or creation if that's your thing, of EC. In the beginning, the skies were without form and void, and the only method of collision avoidance and traffic management was to see and avoid. Pilots seeing other aircraft with their eyes, and controllers seeing aircraft from their towers. And then there were lights. And then the skies were divided into airspace, and ATC saw that it was good and brought forth procedural control, with aircraft reporting their position and calculations made to ensure that aircraft were separated in time and space. Okay, I'll stop that now. Starting from the 1940s, ATC had primary surveillance radar, PSR, to provide an aircraft's azimuth location. Then, fueled by the wartime requirement to identify friend from foe, this was augmented with secondary surveillance radar, SSR, Mode A or Mode Alpha. But the aircraft's azimuth location still originated from primary radar. Next arrived Mode C or Mode Charlie, which provided altitude data. But the aircraft's azimuth location still originated from PSR. This was augmented by Mode S, Mode Sierra, which in its simplest form only adds the aircraft's call sign. But the aircraft's azimuth location still needed to be sourced from primary radar. Mode S brought with it TCAS. Then came Extended Squitter, which cut the apron strings with primary radar and provided lateral positional data from an onboard GNSS source, not reliant on any interrogation from radar. Rather, it's transmitted automatically, it's dependent on an onboard GNSS system, and is broadcast to all, so generically called Automatic Dependent Surveillance Broadcast, ADSB. Therefore, Mode S plus Extended Squitter is an implementation of ADSB. Next came Enhanced Surveillance, where the transponder transmits some additional parameters, and then, most recently, a number of uncertified and unlicensed systems, which various parties, both industry and regulators, are trying to tame and bring together. I'm going to start by explaining the technologies. Don't worry if you don't remember the plethora of technologies and frequencies. A lot of it doesn't really matter when it comes down to what to do, but I'll try to explain what I can, and then that will assist you in deciding what to do. As ever, I'll only be discussing light GA in Europe. Europe's airspace contains some of the busiest in the world. General aviation aircraft, drones, gliders, commercial airliners, and all manner of other traffic all share this space. Even in VMC, where visual lookout remains critical, electronic conspicuity provides an additional layer of safety, especially in poor visibility or high traffic areas, and helps direct the pilot's lookout towards threats. But in IMC, it becomes the principal defense against collision. It enhances the ability to see and avoid other traffic, even when they're not visually apparent. Having said that, there's plenty of evidence, scientific and anecdotal, that we can't see light aircraft further away than about 2 miles, so any alerts of traffic any further away than that can only prepare us for when we need to start looking for it. Furthermore, EC carries the psychological risk that we will feel safe and comfortable and lower our guard if there are no contacts around us. But the reality is that for a host of reasons, such as equipage, incompatibility, technical shortcomings, coverage, and so on, there are likely to be many threats around which don't show up on our screens. If we feel cocooned and don't look out, we could run the risk of air prox or collision. There's also the reverse problem. Because many EC solutions allow us to see other aircraft at very large distances, many tens of miles in some cases, we can lose focus on nearer threats. Please don't get me wrong, being able to see aircraft at 40 miles, such that we can see, for example, runway direction and location of thunderstorm cells, and to position ourselves on the approach with respect to other traffic, are very useful, but that's not the focus of EC. Anyway, I'll come back to usage tips later, but I need to make sure that you understand the technology first. Underlying the issues of EC is that of frequency congestion. There just isn't room to put everything on one frequency as more and more airspace users want to see and be seen. This is made worse by the fact that the use of the standard frequency, 1090 MHz, started way before the digital age and consequently has standardized on a bandwidth-hungry protocol, which means that there isn't enough room for all potential users of today. Not just as adoption goes down market in the manned aviation sphere, but also as UAVs and drones are becoming more widespread. Electronic conspicuity is required in specific airspace, so I'll also be talking about regulatory compliance. Let's talk about technologies used for electronic conspicuity in Europe. The main system used by ATC in controlled airspace remains the secondary surveillance radar, SSR, transponder, which responds to a radar pulse on 1030 MHz by amplifying it, adding information to it, and rebroadcasting it back to the radar station on 1090 MHz. That 1090 frequency becomes really important to our discussions later. Transponders are mainly classified by the information they send back. There are 4 response modes: ground, alpha, Charlie and Sierra mode. Ground mode flags that the aircraft is not airborne, poses no threat to other aircraft and can be filtered out. Larger airports with ground radar use this capability to monitor and control taxiing aircraft. Mode alpha transponders return only the 4-digit squawk code. Mode Charlie additionally responds with the flight level of the aircraft, or altitude based on standard pressure setting if you prefer. All modern transponders include more information and are collectively called Mode S. It's quite frustrating, not to mention a little silly and confusing, that the 2 Mode S standards have the initials ELS and EHS, and they can additionally send ES. The simplest, ELS or elementary surveillance, only adds the aircraft's unique 24-bit ICAO address and the call sign to the received radar pulse as it rebroadcasts it, but does not provide any location data. It's used by ATC to augment primary radar, and it's the primary radar that provides the location information. Enhanced surveillance, or EHS, provides additional flight parameters like selected altitude, that is the altitude that the autopilot has been instructed to climb or descend to or maintain, heading and track, indicated airspeed, ground speed, vertical speed, bank angle and rate of turn, but again does not provide the location of the aircraft. Extended Squitter, or ES, additionally broadcasts the aircraft's GNSS position and velocity. And let's be clear from the get-go that Extended Squitter, or 1090 ES, is the principal source of Automatic Dependent Surveillance Broadcast, ADSB, in Europe. ADSB is so named because it doesn't require any external stimulus, such as ground station interrogation, to transmit. It's transmitted automatically. It does require an onboard location system, such as GNSS, to transmit location data, and it's broadcast because it's transmitted to all and not triggered by receiving an interrogation signal. There's a lot of chatter, which I'll be engaging in a minute, about Sky Echo, UAT and other technologies such as Pilot Aware, but to all intents and purposes, ADSB in Europe is 1090 ES. I emphasize that because before I started making this video, I don't think I had really internalized that, and I'm supposed to be in the higher echelons of knowledge and understanding. Unlike Mode S, Extended Squitter data is broadcast regardless of whether the transponder is being interrogated, so can be picked up by compatible receivers in other aircraft and on the ground, regardless of whether the transponder is being interrogated. This makes it particularly useful when out of range or below radar coverage. Both ELS and EHS transponders are available with extended squitter, but as ES is a requirement for the same aircraft and airspace as EHS, it would be unusual to encounter an aircraft with EHS but no ES. EHS and extended squitter are unlikely to be mandatory for most PPLIR members, as compliance in Europe is limited to aircraft above 5,700 kilograms or a maximum true cruising airspeed of 250 knots. Generally, to operate under IFR in Europe, it's mandatory to carry working Mode S with at least ELS. Mode S is also mandatory in some transponder mandatory zones, even under VFR. Generally speaking, and rules do vary across Europe, it's permissible to fly an aircraft without a transponder outside controls airspace under VFR. But if a transponder is fitted, it must be switched on to its highest capability, i.e. Mode C must be used if it's fitted, whenever the aircraft is in flight. And finally, existing Mode A and C transponders can still be used outside controlled airspace in some countries, but they cannot be newly installed into any airframe, including those in Annex 1, such as historical and experimental aircraft. While transponders were originally developed for ATC, using primary surveillance radar to be able to see and identify aircraft, systems for aircraft to see and respond to the transponder and other aircraft soon followed. These systems are called Traffic Advisory System, TAS, and Traffic Collision Avoidance System, TCAS. There are technically 3 levels of such systems, TCAS 2, TCAS 1 and TAS. But the difference between TCAS 1 and TAS is so subtle, mainly related to regulatory requirements and cost, that I'll lump them together and refer to them as TAS. And if I refer to TCAS, I mean TCAS 2. TCAS is not used on the kind of aircraft used by PPLIR members, so I'll only describe it in as much as it affects us. TAS uses an array of aerials to interpret tiny differences of pulse phase and arrival time to triangulate the position of other aircraft. The TAS system broadcasts an interrogation signal and uses the time of flight of the outgoing pulse, processing time at the other aircraft's transponder, and the return time of flight to calculate range, and phase information and differential timing to measure azimuth. Given that the pulses are travelling at the speed of light and that the aerials are only centimetres apart, I find it quite incredible that they are so accurate and reliable, but so they are. Blips are shown on a screen in the cockpit to represent other aircraft. These are shown in a variety of contexts: dedicated instruments, on the navigator and PFD and MFD in 2 dimensions, or on the PFD in 3 dimensions. The blips are normally accompanied by a relative altitude above or below your level, altitude trend, either climbing or descending, and, when accompanied with extended squitter information, can also show call sign and ground speed. If the other aircraft has no altitude encoder, then the screen will only show position with no relative altitude. In addition to showing the position of the traffic on the screen, if it considers that the proximity and track of the other aircraft represent a threat, the TAS system will generate warnings, called traffic advisories. It's up to the pilot to decide how to respond to these advisories. This is the main difference between TAS and TCAS. Although we don't use TCAS, we do need to be aware that TCAS-equipped aircraft get resolution advisories on us. They will be told to climb or descend, or possibly to stop their climb or descent, and they're obliged to do so irrespective of any ATC instructions or clearances. This can cause all sorts of disruption, not to mention paperwork, and is best avoided. If we do not follow precisely our clearance or get too close to controlled airspace, we can trigger a TCAS RA even if we're not TCAS equipped. Before we leave transponders, a word about multilateration, MLAT. MLAT uses a network of geographically separated ground stations to find the position of aircraft with transponders based on difference in response time to different stations. 2 MLAT stations can place an aircraft on a line. A third station may be able to locate it if all 3 stations are ideally positioned, but generally 4 stations are considered the minimum to pinpoint it. Thereafter, the more ground stations able to see a transponder, the better. There are many different MLAT networks in Europe. Some state-operated, such as Eurocontrol, DFS and NATS. some private and some volunteer-based, such as Flight Radar 24, ADS-B Exchange, Plane Finder, Pilot Aware, and many others. It's my understanding that each MLAT network is independent and does not share data directly to enhance overall MLAT, though many of them, such as Flight Radar 24, publish their output on the Internet. MLAT is able to use mode alpha Charlie signals and the time difference of arrival, TDOA, technique to determine location, but it's at its best on mode S. To illustrate the variability of MLAT, as I make this video, I'm watching on my other screen a friend flying just off the south coast of England in an aircraft equipped only with mode S, no ADS-B. Flight Radar 24 picked him up for about 1 minute, then lost him altogether. And though I can see him clearly and continuously on Safe Sky and Plane Finder, they show completely different tracks and speeds. MLAT is just not a reliable method. Flight Radar 24 states that the lowest usable altitude for their MLAT network to work usefully is between 5,000 and 10,000 feet. As I said before, extended squitter on 1090 MHz, 1090 ES, is one implementation of an application called ADS-B. Extended squitter is just one manifestation of ADS-B, though, in Europe anyway, the predominant one. ADS-B broadcasts your aircraft's position, derived from GNSS, and you can also receive similar data from other ADS-B equipped aircraft. Your transmission of ADS-B is called ADS-B out, and if you receive ADS-B information, it's ADS-B in. Each is available independently of the other. For example, if you use extended squitter on a Mode S transponder, that's just ADS-B out. And if you use a product such as Pilot Aware or Goltzer, that's just ADS-B in. Additionally, most TCAS receivers also have an ADS-B in capability integrated to produce one blip, regardless of how it's been detected. However, there are products which do both ADS-B in and out. This includes some Garmin transponders, such as the GTX 345 series, and a standalone box, Sky Echo. As far as I know, Sky Echo is the only standalone device permitted to send ADS-B out on 1090, and even then only at very reduced power, designated DF18. Whereas a certified installed transponder with 1090 ES, designated DF17, might be visible at 200 nautical miles, the low-powered Sky Echo is likely only to be visible at about 5 nautical miles. Furthermore, I believe that the only European country where it's permitted to be generally used for transmission is the UK, though individual permission may be available in EASA states. Hence, if you fly an aircraft with a transponder with extended squitter, Sky Echo serves no purpose in broadcasting your position. Transmissions from 1090 ES equipment installed in the aircraft are higher power and use external antennae to produce a much greater range and sensitivity than a portable unit. If you'd like to know how effectively your aircraft is transmitting its ADS-B position, you can go onto the Pilot Aware Vector site, there's a link in the description, type in the unique ICAO hex ID, which you can get from your registration documents or many online databases such as the UK CAA, G-Info, ADS-B Exchange or Flight Radar 24, and select the type of transmitter with CAP 1391, the code for Sky Echo, and you will see a polar diagram of the strength of signal in different directions as seen by their atom network, which can help you recognize shading by elements of the airframe. This works best in the UK, though the atom network is expanding coverage across parts of Europe. As I said a moment ago, ADS-B information will appear on the navigator and MFD-PFD if it's received by integrated certified equipment such as TCAS and transponder, but will typically appear on your iPad if it's received from uncertified standalone equipment such as Sky Echo, Pilot Aware or Goltzer. Either way, you will still get warnings similar to traffic advisories. However, ADS-B data can be treated differently depending on how trusted is the source of the GNSS position. The measures of this trust are called SDA and SIL, and they depend on whether the source is approved and its precision. SIL is fixed for an installation, whereas SDA varies with the current performance of the source. There's a huge amount of discussion about this on the PPLIR forum, and the regulations differ in different countries. The bottom line is that many ADS-B receivers, including those at ATC units, and some TAS receivers, will not see and report uncertified devices, which strikes me as a prime example of the perfect being the enemy of the good, as a blip which is wrong by a few hundred meters must be better than no blip at all. There is increasing use of ADS-B in ATC units following the US experience, and those units will only see certified signals. They will not see Sky Echo and probably not where uncertified GNSS is fed into certified transponders, which I'll discuss in a moment. ADS-B returns will typically be shown with a differential altitude, an altitude trend, a track vector, and, configurably, call sign and ground speed, though it might be necessary to click on the return to get this information. In many systems, the return will change colour if a potential conflict is calculated. ADS-B warnings may be very late if the other aircraft or you change direction or altitude suddenly, either because one or the other of you is performing aerobatics or other manoeuvres such as steep turns, stalling or spinning. It's not uncommon for ADS-B returns to have no call sign, presumably because it's not been set in the transmitter. Of course, there are several reasons why traffic does not show. In many cases because an aircraft is not broadcasting its position on ADS-B, but also because the transmitter or receiver is blocked by airframe or topography. In Europe, all certified ADS-B traffic is on a common radio frequency, which is the same frequency used by transponders, 1090 MHz. In the US, there's a second frequency of 978 MHz approved for light aircraft flying below 18,000 feet, which is why you'll see ADS-B equipment advertised as dual frequency. But many national authorities in Europe do not currently approve the use of 978, though discussions are taking place as we speak. Watch this space. Transponders and ADS-B are regulated and mandated technologies, but there are other unregulated protocols in place, notably FLARM, Pilot Aware and FANET. These all use the unregulated but unlicensed 860 MHz band, specifically between 868 and 869.525 MHz. The benefit of the 860 MHz band is that it uses modulation and protocols more modern than used in 1090 MHz, so has a far greater capacity. As the 860 band is unlicensed, there's also much greater opportunity for rapid innovation so long as the national telecommunications standards are met. The 860 band was introduced for and is used by non-aviation applications such as the Internet of Things, industrial, scientific and medical applications. FLARM was originally developed for gliders and is in widespread use in that community. Some light aircraft do also use it, but ADS-B and Pilot Aware are generally favoured in powered aircraft. Because gliders fly relatively slowly and are often circling close together and have limited electrical systems, FLARM is short range, often less than 5 miles. This can mean FLARM traffic suddenly appears close by with late warnings. Generally, it's just safest to avoid areas of known glider activity, which show on charts and NOTAMs. FANET, Flying Ad Hoc Network, is a system rather similar to FLARM used by some paragliders, hang gliders and drones. I have to admit to knowing very little about it, except that it exists. From what I can make out, you can think of it as being another FLARM-type EC. FANET Plus combines a FANET and FLARM transmitter and receiver into the same unit. Pilot Aware uses a proprietary transmission format called P3I. This is only recognized directly between Pilot Aware users, but there are several integrated systems which receive and rebroadcast P3I data. There are many other proprietary systems, each used by a band of airspace users, such as parasenders, hang gliders, drones, or whatever. So, there are many ways that aircraft broadcast their position, at least 5 by light aircraft. transponders and 1090 ES on the 1090 band, and FLARM and pilot-aware P3I on the 860 band, specifically 868 MHz, and, as I'll be discussing in a minute, on the cellular network. UAT on 978 MHz is yet to arrive in Europe. Now, I've distinguished 1090 SSR and ES devices as being regulated, licensed and approved from the 868 devices which are less regulated, but EASA is working on a specification to bring these latter devices into the fold, developing a standard called ADS-L, with L for light. This ADS-L standard would be available for ADS-B 1090, SRD 868, e.g. FLARM and FANET, but also for applications using the mobile network. It's meant to bring together the lighter, lower power transmitters from light aircraft to paragliders to drones and increase innovation. ADS-L, if adopted, will enable drones and other users of very low airspace to be visible, that is conspicuous, in uncontrolled U-space. Many units are able to receive, even transmit, different combinations of these protocols. For example, I've already said that many transponders also broadcast ADS-B using 1090 ES, and TCAS systems generally receive both transponder and ADS-B in. But how does the GA pilot get to see the most integrated view of all the sources? One way is to have a receiver which can see as many protocols as possible. For example, the pilot-aware unit receives ADS-B, transponders and P3I. Sky Echo 2 receives ADS-B and FLARM, and so on. The other way is to use a system which integrates and rebroadcasts all the sources. To some extent this is achieved by products like Flight Radar 24 and Planefinder, but they require a fairly beefy internet connection and are not integrated into our cockpits. It's more usefully achieved by Pilot-Aware and SafeSky, both of which can transmit into the cockpit with a less robust internet connection. Pilot-Aware's Atom Grid rebroadcasts ADS-B, FLARM, Mode Charlie Sierra and FANET Plus, but is only available on Pilot-Aware devices and is rather UK-centric, though beginning to spread across Europe. While within the range of Atom Grid stations, Pilot-Aware is also capable of providing mutual support to relatively local aircraft which are themselves out of range of an Atom Grid. This is rather like an AWACS being able to provide over-the-horizon visibility to low-level aircraft. Pilot-Aware also receives iGrid, which is based on mobile phone connectivity. It sends your position and receives a wide range of incoming traffic information, including ADS-B, FLARM and MLAT SSR, provided you can pick up a mobile signal. Pilot-Aware devices also have the capability of enabling 1090 ES ADS-B output by sending a GNSS location into your transponder if it's ES capable, as are many TRIGs and FUNKers. As I said before, while this provides a good strong 1090 ES signal, it may be filtered out by ATC and other systems because the SIL is 0, indicating there's been no signal integrity checking implemented. If you're not a Pilot-Aware user, the best integration available through an internet connection is from SafeSky. SafeSky captures ADS-B, FLARM, FANET Plus, Pilot-Aware and MLAT transponders, as well as other protocols from the free flight community. Its Mode S capture is somewhat limited because it must be triangulated by multiple MLAT stations, as I said before. And you can sometimes see aircraft with Mode S but no ADS-B pop in and out of view. And it cannot see Mode Alpha at all, but one way and another it sees most stuff. Its advantage is that because it uses unsecured low-level UDP rather than TCP, which is used by HTTP protocol we're normally used to, it works on the weakest mobile internet connection, even 1 bar of edge, which means it works airborne when other systems don't. But it's still at its best low-level and over land. In some ways, that it works best at relatively low level over land is mitigated by the fact that most air proxies occur at low altitudes, mainly in or near airfield circuits, and over popular sightseeing spots, and these areas are well covered. Shortly coming to market is a version of avionics' Aero Tracker with Safe Sky incorporated. This will have an integrated roaming SIM and multiple high-sensitivity aerials that should give the best of all worlds, and there are also moves to improve mobile reception in the sky, but only time will tell. Until you have that self-contained box, you are dependent on your phone or tablet, and I'm about to make myself very unpopular in some quarters, but it has to be said, because there's evidence to show it, if you're depending on a weak signal in a difficult environment, iPhones outperform almost all other devices, being matched only by the highest premium phones from other manufacturers such as Samsung and Google. A budget Android phone will simply not receive signals where top-end phones will. Airborne internet connectivity may take a further stride forward if and when satellite internet becomes more widely and reliably available through Starlink and similar services, and when more cellular networks allow airborne use. Safe Sky integrates directly with moving maps such as SkyDemon, 4Flight and Garmin Pilot using the GDL90 interface, such that the traffic it picks up is displayed on the moving map. But in that configuration, you'll see no traffic when you have no internet connection. To do that, you have to use an intermediary device, such as Sky Echo, and that entails connecting from Safe Sky to the ADS-B device, and then to the moving map, which creates a world of flakiness, as everything has to be set up just right, and it has no resilience to any temporary break in the chain. There's a cumbersome pre-flight sequence every flight. As Pilot Aware and Safe Sky are both commercial operations, both run by dedicated individuals who wish to make the world of aviation a better and safer place, I have to be very careful comparing their products, as I really don't want to devalue either of them. They're both doing a great job, but I will try to distinguish so that you can take your own decision as to which suits you. Safe Sky has an obvious price advantage. Its most basic implementation is completely free, but functionality is limited to seeing traffic within the app on your phone or tablet. If you want to see it within your flight planning app or connect it with Sky Echo or other devices, you have to pay for premium, but that's still very cheap at €40 per year. Safe Sky integrates a host of traffic information from many sources. It works equally across the whole of Europe. However, it's dependent on a mobile signal, and once that signal is lost, all traffic data is lost. If linked to Sky Echo, it will integrate ADS-B traffic received directly by that device and also pass that traffic on to other Safe Sky users. Sky Echo will also send a low-power ADS-B 1090 ES signal, so you can be seen at short range by other aircraft able to receive it. Pilot Aware has a higher entry cost of around €700 to €800 depending on options, and a recurring cost of €30 per year. This provides direct detection of ADS-B and of other Pilot Aware devices, regardless of connectivity. The capability is greatly enhanced if the aircraft is in range of the Atom network, which is very extensive in the UK and has some rather limited presence in France, Germany and Spain. It will pick up MLAT, ADS-B, FLARM and FANET Plus traffic when not in range of the Atom network, but, like Safe Sky, only if it has mobile connectivity. If you have an ES-capable transponder, Pilot Aware can be used to feed GNSS data in to enable 1090 ES. If you don't have either Pilot Aware or Safe Sky, there are a plethora of ADS-B receivers you can use, but then you are limited to only receiving ADS-B 1090 ES data, which will come from any aircraft so equipped, and, in the UK, Sky Echo users. So, how should we operate our flights with EC? What I mostly use it for are circuit traffic. Obviously, you can't rely on everything being visible, but if you are using Atom or Safe Sky, or TAS with ADS-B in, a lot does show up. There are some circuits, White Waltham to the west of London, and some Swiss airfields where aircraft just emerge from valleys spring to mind, where I feel very uncomfortable unless I can see traffic and align what I see with what I hear. General VFR en route awareness. You can't reduce your scan because so much traffic does not show up, but it can help focus your attention. If you can see FLARM traffic, whether directly on your device or relayed by Atom or SafeSky, it can help you route away from milling gliders, both overhead their sights and on competitions. As I said before, FLARM is very short range, so this is where the relays really come into their own. IFR situational awareness. For example, to see why ATC is placing restrictions on me and to allow me to ask for level changes once conflicting traffic has passed. Quite often, you'll be flying on own navigation and then will be put on the heading you're already flying anyway. This is to allow ATC to reduce separation, typically from 5 nautical miles to 3 nautical miles, and it's helpful and interesting to monitor this as it happens. Of course, in controlled airspace, almost everyone has Mode S, and most of them have 1090 ES. Traffic avoidance in poor VMC and IMC outside controlled airspace. Obviously, this is mostly a UK thing, as flying IMC IFR outside controlled airspace is the norm rather than the exception. But when you do, being able to see other traffic and change track to avoid their apparent intentions is very reassuring, though, as I keep saying, there has never actually been a collision in IMC outside controlled airspace, but let's keep it that way. IFR positioning, seeing where other instrument traffic is on the approach, etc., and seeing what other traffic is doing. For example, what runway is in use, how they seem to be avoiding weather. We all have our own experience of how we see EC. In my Navajo, I see TCAS and certified ADS-B on my PFD, MFD and Navigator, and Sky Echo with SafeSky at lower altitudes on Sky Demon and on my iPad. I'm continuously scanning both as traffic appears from different sources on each of them. In theory, both systems should be picking up the same traffic, but that certainly is not the case. It's much more intuitive to see traffic on the iPad as you can compare it better with surface features, traffic patterns and instrument procedures. There's a GASCO study for the UK CAA recommending the use of auditory alerts to allow you to maintain a visual scan and only to have your attention drawn to the EC when there's a threat. I have to say that doesn't suit me. I have the traffic, both TAS and iPad, in my scan all the time. But clearly one size doesn't fit all, and GASCO have put in a lot of research into the topic. If you do use auditory alerts, I do recommend having a way to mute them, as they can become distracting at times. This can be at its worst on final approach when someone at the holding point turns on their transponder or ADS-B, thus giving you a sudden traffic alert at very close range. Technologies like Flight Radar 24 and SafeSky are becoming increasingly used at airfields without formal ATC services. They provide situational awareness to flight information and air-ground operators, such that general information can be given to pilots and runway occupancy can be planned. National authorities generally recognise the benefits of these technologies, especially for enhancing situational awareness. The attitudes of national authorities towards such technologies are generally positive, as they contribute to safer skies, but they do maintain a cautious approach to ensure these tools are used appropriately and in conjunction with other safety protocols. For example, the UK CAA has recently issued a notice acknowledging that some airfields without ATC may consider using applications like Flight Radar 24 to enhance situational awareness. However, they caution that such unregulated systems may not meet the necessary safety and interoperability standards for air traffic services. They advise that these tools should only be used for non-safety related tasks, such as forward planning, and not for critical operational decisions. Having talked about technologies at length, a brief summary of the regulatory position. As far as I know, no authority in Europe mandates EC outside a controlled airspace above 500 feet. But in several countries, notably Spain, Italy and France, areas with high levels of UAV activity are shortly to be designated U-space, and in that airspace, aircraft will be required to transmit either ADS-B or ADSL, as I discussed earlier. If you have a transponder, it must be used at all times to its fullest capability. Importantly, if it's equipped with Mode C altitude reporting, that must be switched on unless ATC instruct you to switch it off. Other transponders which have ground mode must be switched onto that mode when on the ground and only switched to alt mode shortly before takeoff and set back to ground shortly after landing. In many installations this is achieved automatically, either with weight on wheels or ground speed, but it remains the pilot's responsibility to check that the mode changes have taken place. More recent transponders should have alt mode selected at all times, and the software in the transponder will determine the mode, such that ground movement radar can see the aircraft, but it won't trigger traffic alerts to traffic on takeoff or landing. There are software updates available for some transponders to move them to the newer standard, and these should be applied. This situation is in transition, and you should know how the transponder works in any aircraft you fly. Inside controlled airspace and in some TMZs, Mode S is obligatory. This must be supplemented with ES and EHS in aircraft which can cruise at 250 knots or weigh more than 5,700 kilograms. Mostly, there's no requirement in Europe for lighter, slower aircraft to carry ADS-B out equipment, though it is, of course, a very sensible precaution. The only example I know of an ADS-B out requirement for all users, regardless of weight, was introduced in parts of the Amsterdam airspace over the North Sea in 2016. So, while electronic conspicuity is a powerful tool, it has limitations. Not all airspace users are equipped. Some drones, ultralights, older and lighter aircraft may not have any EC systems. GNSS and ADS-B signals can be obstructed in certain conditions, such as mountainous terrain, but also by aircraft structure, particularly if there's no external aerial. You must therefore always complement EC with a disciplined visual scan. As I said, the UK CAA have produced an excellent video on how to integrate EC and see and avoid, link in the description. I do hope that's been helpful and filled a few gaps in people's knowledge and understanding. See you in the next video.